Ever wonder what's really going on inside an AI's brain? You know, how it goes from being completely clueless to, well, getting things right. The secret? It's not just a bunch of fancy code. Nope, it's actually a centuries-old type of math. We're talking about the hidden engine behind pretty much all modern tech, calculus.
So, let's just dive right into the big question, right? How does a machine actually learn? I mean, it can feel like magic, but it's really just a super logical process. It's all about one thing: being able to measure its own mistakes and then correct them, step by step.
And the answer is, honestly, pretty cool. A machine learns because it speaks the language of change, and that language, the mathematical tool that lets us measure and improve anything that's changing, that's calculus.
Okay, so to really get a grip on how AI works, we've got to understand the language it's speaking. And believe me, calculus isn't just for physics class anymore. It has become the language of modern technology.
I mean, think about it. The whole learning process for an AI, it's all about change, right? It's about growth. You've got this system that starts out kind of dumb, and it's constantly trying to move to a better, smarter state. Well, calculus is what gives us the tools to manage that whole journey. And that journey has a destination. We call it optimization. It's all about finding the absolute best possible outcome.
So how do you actually optimize something? Well, first things first, you have to be able to measure how it's changing. And for that, we have maybe the most important tool in the entire calculus toolbox, something called the derivative.
Okay, the easiest way to think about a derivative is like a speedometer for a function. Your car's speedometer tells you your exact speed right now, at this very instant. A derivative does the same thing, but for a mathematical function. Let's say the AI's error rate. The derivative tells us, is the error getting bigger or smaller right this second, and by how much?
All right, let's tie this back to our AI. The derivative is basically the slope, right? So if the slope of its error is positive, that means the error is going up. That's bad. If the slope is negative, the error is going down. That's good. We're headed in the right direction. But the real magic moment, the thing we are hunting for, is when that slope is exactly zero. That means we've hit a flat spot, the very bottom of the valley, the point of minimum error.
And that hunt for the flat spot, that's the whole game. This is where all that math theory turns into a super powerful practical tool for finding the best solution to, well, just about any problem.
So this leads to the million-dollar question, right? How do we actually tell a machine to find that lowest point? How does it search through this massive landscape of possibilities to land on the absolute minimum error? The answer is beautiful in its simplicity. We tell it to do this: find the exact spot where the slope, the derivative, is zero. That's it. That one little equation is the mathematical command for find the bottom of the valley. It's the entire goal of the learning process, boiled down to its absolute core.
Okay, so we've got the theory down. Find where the slope is zero. Now let's connect the dots. Let's see exactly how an AI puts this idea to work to actually learn. This is where it all comes together.
The algorithm that makes all this magic happen is called gradient descent. And I'm not exaggerating when I say this is the engine that drives pretty much all of modern AI. It's the real-world application of everything we've been talking about. It uses derivatives to minimize what's called a loss function, which is just a fancy term for a store that measures how wrong the AI is.
The best way to wrap your head around gradient descent is to imagine this. You're standing on a huge hilly landscape, but it's completely covered in thick fog. Your goal is to get to the lowest possible point. So what do? Well, you can't see, so you feel the ground at your feet to figure out which way is downhill, right? That's the gradient. Then you take one small step in the steepest downward direction, and you repeat. Feel the ground, take a step. Feel the ground, take a step. You just keep doing that over and over until you literally can't go down anymore. You're at the bottom. That is exactly what an AI does, adjusting its own settings with every single step, getting a tiny bit smarter each time.
And let's be super clear here. This isn't just some nice-to-have tool. It is absolutely essential. Without the ability to figure out that slope and take those little steps downhill, the whole learning process for a neural network, it just doesn't work, period.
Now, gradient descent is an amazing use of this stuff in AI, but this whole way of thinking, this language of change, is so much bigger than just that. The ideas behind calculus are like a universal toolkit that's used all over science and technology.
So far, we've only been talking about one side of calculus: differentiation. That's the part about finding the slope to go downhill. But calculus has an equally powerful partner: integration. If differentiation is about breaking things down to see how they're changing right now, integration is about building things up to see the total result. It's like, instead of finding your current speed, you're calculating the total distance you've traveled. They're really just two sides of the same incredibly powerful coin.
And this full toolkit? You find it everywhere. I mean, it's used to model the motion of planets in physics, to price complex options in finance, to create those mind-blowing animations in computer graphics, even to model how populations grow in biology. Calculus really is the foundational language for describing and improving the world all around us.
So if there's one single thing you take away from all this, let it be this. Calculus is the engine that drives optimization. It doesn't matter if you're trying to minimize the error in an AI, maximize profit for a company, or find the most efficient flight path for a spaceship. You are using the fundamental logic of calculus.
Which kind of leaves us with one final big thought. If calculus gives us the power to model, measure, and improve pretty much any system that's changing, what problems out there can't be made better by speaking this language of change?